The aim of the project is to construct a materially disposable rocket using a set of lightweight plastic and cardboard pieces to create the shaft, the fins, and the nose cone of the rocket, along with the parachute and the engine bay. Then calculate the forces being applied to the rocket, considering the current state of motion. Work out the velocity, the acceleration, and the height of the rocket at set certain intervals, being calculated in mass with an Excel spreadsheet. Calculate the maximum point of kinetic energy being exerted from the rocket, along with the total energy / potential energy of the rocket. And finally, to graph the motion of the rocket, including the velocity, the acceleration, and the height of the rocket at certain intervals, from launch to apogee. Through the duration of the experiment, the rocket will be in 4 separate states of motion. Firstly, in rest while it's still at the launch pad. Secondly, as the rocket launches and the rocket has upwards thrust. Thirdly, as the rocket runs out of fuel and is coasting upwards until the parachute opens. And finally, the rocket's slow parachute descent down to the ground. While the rocket is on the launch pad at rest, the only forces are gravity, along with the normal force upwards. After the rocket is launched, the effects of the force of gravity remain, along with the drag from the air and the thrust of the rocket upwards. This force overcomes gravity and drag, making the rocket accelerate upwards. When the rocket runs out of fuel and the acceleration stops, the rocket will coast upwards with only the force of gravity and drag being applied, slowing down the rocket until the velocity is equal to 0 and the parachute is deployed. The rocket will start to fall downwards, with gravity and drag still being the only forces being applied, but the drag on the descent will instead cause the rocket to not accelerate at 9.8 meters per second square, as the increased surface area of the parachute creates a drag coefficient to have a much higher value.
To determine the total energy in our rocket, we look at the time when its velocity is highest. At 0.5 seconds, our rocket engine has just finished delivering all of its thrust, so it is at this point when our velocity is highest. To get our total energy, we simply record the height of the rocket at this time, so we can calculate our gravitational potential energy also. The sum of these two gives us the total energy of the rocket. With a maximum velocity of 39.2 meters per second and a mass of 52 grams, the total kinetic energy of the rocket is 44.2 joules. The height of the rocket at this moment is 10.3 meters. This results in a 5.9 joule gravitational potential energy, giving our rocket a total energy of 50.2 joules. To calculate the stability caliber of our rocket, we use 3 pieces of information: the center of gravity, the center of pressure, and the maximum diameter of the rocket. While center of gravity and maximum diameter refer to concepts most of us understand, center of pressure is a little less common metric. The center of pressure is the point about which the forces of air pressure act on the rocket as it passes through a fluid, or in our case, air. For our rocket, the location of the center of gravity and the center of pressure are 18 centimeters and 14.5 centimeters respectively. When the difference between these two lengths is divided by its diameter, 2.5 centimeters, we get our stability caliber, which is 1.4 in our case. Using the previously derived formula for acceleration, we were able to determine the acceleration over each period of the flight. The first image shows the acceleration while the engine was running, starting high but then decreasing as drag increases. The second image shows the acceleration while the rocket is coasting. It is now decelerating as there is no longer thrust. The rate of the deceleration decreases as velocity decreases. The third image shows the acceleration with the parachute deployed. Drag is now opposing the wake force and reduces the deceleration to near 0 as the rocket approaches the ground. We calculated the change in velocity as acceleration times the difference between time increments. We then added the change in velocity to our previous instantaneous velocity. Using Excel, we were able to do this for the entire flight of the rocket. The first image shows the velocity while the engine was running.
it can be seen that it is increasing at a constant speed. The second image shows the velocity decreasing at a near constant rate as there is no longer any thrust. The third image shows the velocity while the parachute is out. When the velocity reaches zero, the rocket is at its apogee and begins returning to the ground. Its speed downwards is quite slow due to the drag of the parachute. Our expected maximum speed occurs at the end of our powered flight and is equal to 39.06 meters per second. We calculated change in height as the difference between time increments divided by 2 multiplied by the velocity of the previous time increment added to the current velocity. We then added this change in height to our previously calculated height to generate height values for each increment of the flight. The images show the height of the rocket throughout the launch, gaining height throughout the first 2 phases and reaching its maximum just after the parachute deploys, before then returning to the ground. Our expected maximum height was at 76.18 meters from the ground. Using the manual altimeter, we were able to determine that our rocket reached its peak at 64.97 meters. There's a 12-meter discrepancy there, but that may be due to the inaccuracy of the altimeter.